So there's one thing that's still missing from the discussion that we've given on the physics of heat within food, and that is, what is it that determines the distribution of heat inside of a food? If this is a piece of steak, we know that if we cook it in the oven, that over time the temperature distribution will have some functional form, it will have some behavior, and since what we're actually trying to do is hit target temperatures, as we've discussed now for this week, one would like to know really what is the physics of setting up this temperature distribution and what does it actually look like. So it turns out that doing this is a bit of an advanced topic in the sense that it requires more mathematics than we are going to include in this class. And in particular, in the last video we discussed basically, how one computes the rate of change, right, of the thermal energy of the food. We said that that was the derivative of mCp delta T, and we explained basically how the rate of change of thermal energy could be set equal to the rate at which heat is coming from the oven, and that could give us an equation for the temperature in the center of a steak. So it turns out that this same type of perspective in deriving an equation like this, if one uses a bit more calculus, one can derive an equation that is very popular among scientists, and it goes by the name of the diffusion equation. And this equation actually allows you to actually compute on first principles the distribution of heat within a food. And I'm going to just show you the equation just so we can all admire it. I mean, in science classes, often you're forced to admire an equation that you don't fully understand. And so why should we be any different? Let's just look at it right now. So here is the diffusion equation. What it basically says is that the rate of change of temperature in the food is equal to this. And I'm not even going to explain what this means. It's just an equation. You're supposed to admire it for the symbols. And so this is an equation which actually has specific meaning, though, for scientists. And in particular, it is possible, with a little bit of effort, to program a computer to solve this equation for you. And if you do that, then what the computer will actually give you is a plot in which you actually can compute as a function of time the distribution of temperature, how the temperature depends on x, which is some spatial coordinate inside the food. So you can actually calculate from first principles what we've been talking about this week, namely that you start out with food that is cold, that is at room temperature, so this is at 23 degrees or so, and then over time the temperature increases and the food eventually becomes cooked. You can actually calculate these types of distributions. And the value in this is that if you can do that, then you can actually really see how the different types of heating protocols that we talked about at the end of the last lecture, namely the heating protocols of our friendly chefs, Carme, America's Test Kitchen, Nathan Myhrvold, and so on, how those heating protocols that they use for a steak lead to different temperature distributions in the steak, and how that leads to different levels of doneness in the food. So the only thing that's missing to be able to do this is to have a computer program that actually solves this equation for the temperature distribution and allows us to play with the different cooking methods. Now, fortunately for us, a group of MIT undergraduates, along with their faculty sponsors, in preparation for this edX class, were able to actually write a piece of software that we can use to actually solve the temperature diffusion equation and to use it to try to understand the differences between the ways that the different chefs cook steak. And we're now about to show it to you and to use it to just examine the different temperature distributions that we have. But I want to, before showing you how this works, how the software works, and then using the software to actually find out what the temperature distributions of the steak is, I want to just tell you a little bit more about how this program that they wrote works. So by solving the diffusion equation, you can find the temperature profile, but what we want to do is to translate that temperature profile to how well the steak is done. And in order to do this, what we've done in this software is to use a cooking table for temperatures and doneness of both meats and fish that we took from Harold McGee's On Food and Cooking. And this cooking table is really just in itself a rule of thumb, and it looks something like this. So we have a table where basically what we do, and we're going to make a table for a different type of food. So I'm going to just sort of show you a table that applies to steak. So this is steak, okay? And basically what we do is we have target temperatures. So here I'm going to write T target, and then I'm going to have a description of how the steak is done. So, for example, what we're going to say is that if the temperature of the steak reaches 50 degrees Celsius, that's going to be called a rare steak. If it reaches 60 degrees Celsius, we're going to call that a medium steak, and so on. And so for a steak, there are slightly higher temperatures at which it becomes well done, and so on. And what we've done is just taken essentially an eyeball guess of these different target temperatures, and then you're going to see in the software is that the software will calculate the temperature profile using this mathematics, and then it will just say that when the temperature gets above the target, the steak cooks to varying degrees. And of course, the important thing about cooking, as we've described, is that cooking involves protein, transformation of state. And so, whereas if you heat something up, if you then cool it down, it cools down. If you heat something up to 60 degrees Celsius, if you heat a steak up to 60 degrees Celsius, within our model, the way that we're going to calculate it is we're going to say the steak is then medium, and even when you cool it down, it's still medium because the proteins have actually transformed themselves appropriately. And what we use in the software that we're going to now show you has actually different cooking target tables for steak, fish, and turkey. We didn't put in a lot of effort to refining these numbers to make sure they really correspond carefully to what you see and do in the kitchen. But really our point of this is to basically start to give you more intuition for how the temperature distribution changes as a function of time within a food, and to give us a way to actually compare the different cooking methods that we've seen.